students, you're welcome to this session of Unit 3. The unit is about volumetric analysis, which is a quantitative tool in which we will be measuring volumes accurately to determine the quantity of solutes in a solution. This very session looks at definition of terminologies in volumetric analysis, selection of indicators, and standardization of solutions. The objectives are to distinguish between equivalence points and endpoints in a titration exercise, distinguish between titrants and analytes in a volumetric analysis, distinguish between standard solution and primary standard solution, select appropriate indicator for an acid-base titration, and finally, standardize an acid or base using volumetric analysis. So let's look at the terms that we have mentioned in our objectives. One is volumetric analysis itself, and with volumetric analysis is a quantitative method or tool which involves accurate measurement of volumes of solution to estimate quantity of solute particles in a solution. In titration, there are terms that you would mention. One is equivalence point, which is a point in the titration reaction at which an equivalent amount of the base and acid are neutralized. Another is the end point, which usually in the lab we say when there's a color change, then an end point has been reached. That is when you are using color indicators. The end point is a point in the titration reaction at which the base has been completely neutralized by the acid, or the acid has been completely neutralized by the base. Let's proceed. The next one is the titration itself. What is the titration? It is the process of estimating the concentration of a solution of a substance by reacting it with standard solution of another substance. Now you should know that the titration is a tool that we use in various analysis, but basically we are estimating concentration of solution. Okay. In the titration, we would hear of standard solution, and it's a solution of known concentration, or a solution whose concentration is accurately known. Another term is primary standard solutions, and they are solutions which are usually prepared by weighing and dissolving certain solid reagents in water to obtain accurate concentration of solutions. So, an explanation of terms. Now, standardization, which is the process of determining the accurate concentration of a solution by titrating it against a primary standard solution. In the titration, once again, you will hear of the titrant and the analyte. The titrant is a solution whose concentration is known in the titration, whilst the analyte is the one whose concentration is unknown. And the titer is the volume of the solution in the burette, which has reacted with the other solution in the conical flask at the end point. These are terms that we'll be meeting a lot in the session. And we will need indicators to tell that endpoint has reached. You see, the acid is colorless, the base is colorless, and when we have equal amount reacted, it will still be colorless, and we cannot tell. One thing that will help us is using indicators which would be changing colors for us to know that, okay, at this point we've had estimatedly this amount consumed and that. So indicators are weak organic acids or bases which change color in acid or alkaline medium depending on the pH of the solution. So our next task is to consider the choice of indicator in a titration. You cannot just pick any indicator at all. Because you are doing acid-base titration, any indicator will do. You just pick and you proceed. You may not make accurate recordings, or you may not get accurate values. So to do that, you need to consider the strength of the acid or the base in order to select the right indicator. So here is a guide. When you are titrating a strong acid against a strong base, then indicator that can work in both the acidic region, or indicators that can work in acidic region or basic region, can be used. There are a number of indicators, color indicators, but two that are very common are the methyl orange and the phenolphthalein. And these ones, when we are doing strong acid against strong base, we can use any of them. When you are titrating acidic or strong acid against weak base, the solution will hydrolyze to give an acidic solution. And in this case, if you pick a base which is very good in basic region, it might not give you accurate reading. So we need an indicator that is good in acidic region, that is methyl orange. So methyl orange will work well. And if you are titrating weak acid against strong base, it will hydrolyze, the solution will hydrolyze to give a basic solution. And so we need an indicator that works good in a basic region. Phenolphthalein is good. For weak acid against weak base, no indicator would work well for you. So this will guide us in selection of indicators. Now you have selected your indicators and you have done your titration. How do you record your data? There are some technicalities that you need to take note of. One is that the titration exercise should be repeated two or three times, ensuring that at least two titer values do not differ by more than 0. plus or minus 0.15. So do the titration. In fact, if there is time and resources, you can even do more than the 3. Okay, it could be that the first time you made a mistake, you poured 1, you made a mistake. So the subsequent ones, you take your time and then do well. But make sure that in the trials that you have done, there are at least 2 of them that do not differ much. If they are the same, perfect. If they should differ and you want to use them, then the difference shouldn't be more than plus or minus 0.15 cubic centimeters. All values in the data should be recorded to 2 decimal places. And so if you had a volume of, let's say, 20 points or just 20, you are not going to write 20, only 20 in the table. You write as 20.00. That is 2 decimal places. The volume of the solution in the burette is the average titer value. So the table that you have drawn, the values that you are going to record in are values you are reading from the burette. And after that, when you find average titer, it means you are finding the average volume of the content of the burette used in the titration. The volume of the solution pipette, or the volume of the solution pipette, is the volume of the pipette used. So when you pick the pipette, its volume indicates the volume that you are going to pipette. For instance, if you pick a 20 or let's say 25 cm cubed pipette, then the volume that you are going to pipette is that 20 or the 25 cm cubed that you picked. You don't pick 25 cm cube pipettes and then you pipette 15. Ensure that there are no cancellations on the table. Very important. If you think you have made a mistake, cancel your table and then do again. That's why it's always advisable to get a rough table somewhere to be recording your data there, so that when you make a mistake, that's not the true work you are presenting. But the final work that you are presenting, it shouldn't have cancellations. Don't deepen it as well. So knowing those guidelines, we can now take an example where we assume to do titration, and our focus will be on the calculations. So we have a solution and we have a titration being done. Our task is to calculate the concentration of the acid used. Here, the acid is labeled as E, and we have to find the amount concentration and the mass concentration. We have this table as the values recorded from the burette. The pipette volume has been given. So to do that, we need to complete the table first. And in the table, we have already said something about it. You may do a number of trials. Just make sure that at least 2 of your values are the same or do not differ by a margin of plus or minus 0.15. When you are recording in the table, you should have your final before your initial, because we are finding the difference. We are subtracting what is down from what is at the top. So we have, and check in this table, they are all to 2 decimal places. So we find the difference to get the volume of E, which is the acid used. For the first column, we subtract 0.00 from 24.5, that gives us 24.50. The second, we subtract 24.50. What it means is that when the first titration was done, the volume or the acid in the burette wasn't topped up to 0. The second titration was carried away from where the first one ended. That is why we have the final in the first titration becoming the initial in the second titration. So we find that we get our answers for the volume of the acid, which is E used. The next thing is to find the average volume of E used. So we select, if we have 3 of them that are very consistent or even the same, we select them. In this case, we have 2 of them that are the same. So we just use those 2 to minimize errors. And our average titer or average volume of E used is 24.50 cubic centimeters. The next is to proceed with our concentrations. So the first one, to get our amount concentration, one thing about titration is we'll start from where we know to where we don't know. And usually first principle is good. We were given mass in the question, how the solution was prepared. We're given mass over there. We're given volume over there. We need to find concentration. Remember, we are finding that of the acid, but we need to start from the base, because that's where we have enough data. And since there's a relation between the acid and the base, we can use that relation, that's in terms of moles, to reach the acid. So we find the amount concentration of the base, and when we have that, for example, what we have here is 0.1 mole per dm cube. What it means is that 1000 centimeters cube of the base contains 0.1 mole. So if 1000 cubic centimeters of the base contains 0.1 mole, then the volume that we used will contain what? Now get this clear. It is like a big solution has been prepared in a big container, and the total volume is 1000 cubic centimeters with a number of moles of 0.1. Since we are not going to use the whole of that 1000 and we are going to fetch some, we don't expect that the volume that we are going to fetch is also going to contain all the particles of the sodium hydroxide. Okay, it's like you have fetched, let's say, a cup of sand into a bucket of water, you have stirred it, and then you have fetched some of it. What you have fetched will not contain all the sand that you poured in the bucket of water. It's only going to contain some. So you need to find if the whole of that bucket contains a cup of sand, then the small portion that you have fetched, what will be the quantity of sand in it. So that's what we are doing here. If the whole 1000 cubic centimeters contains 0.1 mole, then the volume that we pipetted, the 25 that we took, will contain what? So when we do this, we are going to get 0.0025 moles. Remember, it is the 25 that reacted with that average volume of the acid that we used. So there is a relation there. Now, knowing this from the equation, we have 2 moles of the sodium hydroxide reacting with that of the acid to give us our salt and water. So if 2 moles reacted with 1 mole of the acid, then this 0.0025 moles of the base, which is sodium hydroxide, will give us what moles of the acid. So if 2 is equal to 1, then 0.0025 moles of sodium hydroxide is going to give us half of, or 1/2 times 0.0025 moles of the acid. So this implies that the corresponding moles of the acid is 0.00125 moles. Now we know the moles of the acid, but remember that was the mole of the acid in the average titer. In other words, for the acid to was standing somewhere, there was a large volume there, and then small volume was picked. That small volume is what reacted with the base, which is the average titer, the 24.50. So now that 24.50 is what contains this 0.00125 moles. If that's the case, then 1000 cubic centimeters will contain what? So we do such relation, and then now we have this amount concentration, and that is the concentration of the acid we are looking for. The next task is to find the mass concentration. But once we know the amount concentration, we know that rho, which is mass concentration, is giving us amount concentration times molar mass. We know the molar mass of sulfuric acid from the atomic masses. We can calculate, and it is 98 grams per mole. We do our substitution into the formula for rho, and then we have 4.9 grams per cubic decimeters. What it means is that 4.9 grams of the acid was dissolved in 1000 cubic centimeters. There is another method of doing that which has been included. Take your time and then go through.